Electric vehicles are everywhere, transforming the way we move through our cities and towns. Their numbers are skyrocketing, with more people than ever choosing electric over gasoline. By 2030, we could see 240 million EVs on the road, up from just 30 million a few years ago. This explosive growth is reshaping the automotive landscape and putting new demands on our infrastructure. Each EV relies on a large, complex battery pack, packed with advanced materials. But what happens when these batteries reach the end of their life? It's a question we can't afford to ignore. Sending them to landfills would create a massive environmental crisis, polluting soil and water, and wasting valuable resources like lithium, cobalt, and nickel that took millions of years to form. Mining these materials is costly, environmentally damaging, and risky for global supply chains. It often leads to deforestation, water pollution, and hazardous working conditions in some regions. That's why recycling isn't just smart, it's essential for a sustainable future. It's the only way to keep up with the growing demand for battery materials. The first big wave of EVs is aging, and by 2030, over 1 million batteries will be retired every year. This number will only increase as more EVs hit the road. Recycling lets us recover precious materials and build new batteries, creating a circular economy where nothing goes to waste, and old batteries become the foundation for new technology. This reduces mining, stabilizes mineral prices, and lowers the carbon footprint of new batteries, making electric vehicles even cleaner. Using recycled materials is far less energy-intensive than mining raw ore, saving energy and reducing greenhouse gas emissions. A strong recycling industry makes EVs truly sustainable, ensuring the shift to electric mobility benefits the planet from start to finish, not just at the tailpipe. Without recycling, we risk trading one environmental problem for another, undermining the promise of clean transportation. The future of clean transportation depends on closing the battery loop, turning today's waste into tomorrow's opportunity, and ensuring our roads stay green for generations to come. When an EV battery reaches the end of its useful life, the recycling journey begins with a crucial first step: careful disassembly. This isn't as simple as tossing the battery into a shredder. Instead, it's a meticulous process that requires patience and expertise. EV battery packs are complex, containing hundreds or even thousands of individual cells, modules, and sophisticated electronics, all tightly packed together. Disassembly is a major bottleneck in the recycling process. It's often done by hand, with skilled technicians carefully navigating the unique designs and layouts created by different automakers. Workers must safely disconnect high-voltage components, drain any remaining fluids, and remove the battery management system, all while avoiding damage to valuable materials. This is slow, hazardous work. Strict safety protocols are in place to prevent fires, electric shocks, or chemical leaks, making the process even more challenging. Once the pack is dismantled, the modules are removed and often broken down further to access the individual cells, the true source of valuable metals like lithium, cobalt, and nickel. Aluminum, copper, and other metals are separated out for conventional recycling, ensuring that nothing goes to waste. Before further processing, the cells must be fully discharged to eliminate any risk of fire or explosion, a step that can take several hours and requires constant monitoring. Only when the cells are completely inert and safe to handle can the core recycling process move forward. This initial phase, collection, testing, discharging, and disassembly, is absolutely critical. It lays the groundwork for every step that follows in the recycling chain. A well-executed start sets the stage for advanced chemical recycling, where valuable elements are recovered and reused. Without efficient disassembly, the entire recycling chain slows down, creating a major obstacle for the industry. That's why streamlining this step, through automation and better design, is key to scaling up battery recycling worldwide. The future of sustainable transportation depends on making these first steps faster, safer, and more efficient for everyone. Once batteries are dismantled, the real extraction begins, mainly through two major processes: pyrometallurgy and hydrometallurgy. These methods are at the heart of modern battery recycling, each with its own strengths and challenges. Pyrometallurgy relies on extremely high temperatures to smelt battery cells, burning off plastics and other non-metal materials. What's left is a molten metal alloy, rich in valuable elements like cobalt, nickel, and copper. This process is similar to traditional metal smelting and is effective at concentrating these metals for further use. However, pyrometallurgy is highly energy-intensive, requiring vast amounts of electricity or fuel. It also often fails to recover lithium, which ends up trapped in a waste byproduct called slag. This slag can be difficult to process further, and managing these byproducts is a significant environmental concern. Hydrometallurgy, on the other hand, takes a different approach. It starts by shredding battery cells into a fine powder known as black mass. This black mass contains a mix of metals, which are then separated using powerful acids and chemical solutions. The process can extract lithium, cobalt, nickel, and other metals with impressive efficiency. Hydrometallurgy is less energy-intensive than pyrometallurgy and can recover over 95% of key materials, including lithium. This makes it especially attractive as battery demand grows and the need for sustainable recycling increases. The downside: hydrometallurgy uses hazardous chemicals and generates liquid waste that must be carefully treated to avoid environmental harm. Managing these chemicals and ensuring safe disposal is a critical part of the process. Most modern recycling facilities now use a hybrid approach, mechanical shredding to create black mass, followed by hydrometallurgical refining. This combination maximizes recovery rates and balances energy use with environmental safety. The ultimate goal is to produce pure battery-grade materials that can be fed directly back into new battery manufacturing, closing the materials loop. Each method has its own trade-offs, but hydrometallurgy is gaining ground for its efficiency, high recovery rates, and ability to reclaim lithium. The choice of recycling process depends on several factors: battery chemistry, economic considerations, and the environmental impact of each method. Innovations in recycling technology are pushing for cleaner, safer, and more efficient methods, aiming to reduce waste and environmental risks even further. The future of battery recycling hinges on refining these processes, making them scalable and sustainable for the next generation of electric vehicles. Recovering every valuable element, from lithium to nickel, is the ultimate goal, ensuring nothing goes to waste and every resource is reused. That's how we close the loop on battery materials, paving the way for a truly circular economy in the battery industry. Battery recycling is complicated by the variety of chemistries on the market. NMC and NCA batteries, rich in cobalt and nickel, are the most valuable for recyclers. Their high-value metals make recycling profitable and offset costs. But lithium iron phosphate, LFP batteries, now popular for their safety and low cost, contain little or no cobalt and nickel. This shift challenges recyclers, as LFP batteries are less lucrative to process. As LFPs flood the market, the industry must innovate to recycle them efficiently and profitably. New processes or ways to add value to recovered materials are urgently needed. The economics of recycling are changing fast. Scaling up battery recycling faces real-world hurdles. Disassembly is slow and costly, as packs are built for durability, not recycling. High-voltage batteries pose safety risks. Electric shock and fires are constant threats. Facilities need expensive safety systems and highly trained staff. The industry is also at the mercy of volatile metals markets. Falling prices for lithium and cobalt squeeze profits. Some recycling startups have already gone bankrupt or scaled back. Ironically, there's also a shortage of old batteries. Modern EV batteries last longer than expected. This mismatch between recycling capacity and battery supply strains the industry. The path to profitability is anything but straightforward. Before recycling, many EV batteries get a second life. Retired from vehicles at 70–80% capacity, they're still useful for less demanding tasks. Companies repurpose them for stationary energy storage, home solar, commercial buildings, or grid backup. This extends battery life by 5 to 10 years and supports renewable energy adoption. Major partnerships, like GM and Redwood Materials, are building large-scale storage systems using second-life batteries. These systems can even power energy-hungry data centers. Second life use delays recycling, easing feedstock shortages and maximizing value. It's a win-win: cheaper storage, less waste, and more sustainable energy. Only after this second life are batteries finally recycled for raw materials. This approach is central to a true circular economy. The challenges of current recycling methods are fueling innovation. Direct recycling aims to restore cathode materials without breaking them down completely, saving energy and reducing waste. If perfected, it could dramatically cut costs and emissions. Green chemistry is also advancing, with researchers testing organic acids and even microbes to extract metals more safely. The goal processes that work for any battery type, profitably, and with minimal environmental impact. As battery technology evolves, recycling must keep pace. The companies that master these new methods will lead the industry. Closing the loop depends on relentless innovation. Policy is shaping the future of battery recycling worldwide. The EU's battery regulation sets strict recycling targets and requires recycled content in new batteries. Digital battery passports will track batteries from birth to end of life, streamlining recycling. China leads with strong producer responsibility laws and a digital traceability system, even importing black mass for processing. The US is ramping up with tax credits and loans to build domestic recycling capacity. These policies create certainty and incentives for investment. Government action is accelerating the shift to a circular battery economy. Regulation and innovation must go hand in hand. The future of EVs depends on a closed-loop battery system. Recycling old batteries to make new ones transforms waste into a resource. By the 2030s, recycled materials could supply over half the industry's mineral needs. This reduces mining, stabilizes supply chains, and cuts environmental damage. Using recycled materials slashes the carbon footprint of battery production. A strong recycling industry makes EVs cleaner over their entire life cycle. Achieving this vision requires automakers to design for recycling, ongoing innovation, and supportive policies. Consumers also play a role by ensuring batteries are recycled. The journey is complex, but the goal is clear: truly sustainable electric mobility. The circular battery economy is the foundation